And you believe that cancer is the biggest disease in the modern world?
Of course, it's one of the biggest killers. It's such an interesting challenge to tackle. You have to think about this whole idea of how do you target a cancer? How do you see the difference between cancer and all the rest of the cells in your body? But actually, with these new immunotherapies, the concept of how to tackle each of these diseases, we are getting a lot closer to being able to treat them effectively.
And so this old model of curing cancer is from the outside in, but now
what the field does is look for specific molecular protein-based differences on the outside of the cell, but they're becoming this whole new field called Hey everybody, my name's Russ.
And I'm Fidit.
And today we are two humans talking about the new technology revolutionizing cancer treatment called immunotherapy. Let's get into it.
Fantastic. Thank you, Ross. You have spent the last 6 years learning about cancer and testing different technologies, and today you have taken the time to teach us as much as possible to people such as myself, average people that don't know much about cancer and cancer treatment. And so I'm going to ask you lots of questions, but hopefully you can teach me.
I hope so. This is, my field. I mean, I don't want to say expert, sounds a little big-headed, but I have worked in this for a long time and I'm very passionate about it. So I hope to have a cool discussion today about some of the really exciting new technologies that are coming to treat cancer. We hear about these all the time in the news, right? These stories, this lab has made this and this lab has made that. But I want to talk about the actual realities of what is coming in the future and why we're about to enter a golden age of cancer treatment. I really do think that.
That sounds extremely exciting. Can you please help us set up the boundaries? For example, can you help me understand what cancer is exactly? Why do people get cancer? And why is it such a deadly disease?
Yeah, it's obviously something we're all familiar with, right? 1 in 2 people will get cancer in their lifetimes. It's a huge amount of people get cancer. Our bodies are basically designed to fight back against cancer for as long as possible. Even the whole aging process, some parts of it are to do with anti-cancer, because what cancer actually is your body cells, essentially anywhere in your body, have lost the ability to control their proliferation, which is to say their growth. They've lost the ability to kill themselves. The technical term for that is apoptosis. But if a cell is in trouble or feeling like it's gone wrong in some way, usually your body cells will kill themselves. They will undergo apoptosis to not pose a danger to the rest of the body, right? They've lost that ability. The third thing is that they've lost their immunosurveillance. They've lost their ability to be seen or recognized in some way by the immune system. So they've hidden away from the immune system, because when they've lost control of their proliferation and they've lost control of their apoptosis, usually the immune system would come and control them, kill them, or shut them off. In some way, they've managed to prevent that from happening. So they've evaded the immune system. So you need at least 3 things to become cancer. These things happen through mutation. So there are genes in your body called oncogenes, and there are genes in your body called tumor suppressor genes. And these ones are, some of them, if they're switched on or mutated or they go wrong, they can cause cancer. And some of them are in your body designed to prevent it. And if they get destroyed or damaged somehow by mutation, they can allow cancer to happen also. So you need kind of some of them to be activated, some of them to be deactivated for that to happen. So let's sum it up really simply. Cancer is cells in your body that have gone rogue. They've started to proliferate and they've essentially become a new entity inside your body made of yourself. That's why they're so hard to treat, because they're made of you. They're made of the same cells as you are. So how do you treat that?
Thank you for explaining it. I think now that I understand the 3 requirements for a cell to become a cancerous cell, I have a better understanding of what's happening. So this process can happen anywhere in my body and at different sizes, I'm assuming. So usually, what are the most common types of cancers that we get, and what is the size that we have, and can I prevent them in any way?
Just to have a quick disclaimer in here, I'm not a doctor, so I'm not a clinician who treats cancer patients by any means. I am a researcher who researches some of these treatments that we're going to be talking about, but I don't know as much about the sort of clinical landscape, would be the way to say it. I couldn't, for example, tell you what cancer is more prevalent than others precisely. Obviously, there are ones that we all hear about a lot, such as prostate cancer and breast cancer and leukemia and blood cancers. These are all common types of cancers. Some of them are easier to treat than others, and depending on the origin of the cancer cell, they have different properties. Maybe it's slightly too technical there with the details for people who aren't familiar with the field, but basically what I'm trying to say is that there are many different types of cancer. Depending on the origin of them, they can have different ways of targeting them or tackling them. And in terms of what you can do to prevent cancer or make yourself risk-free, you cannot never eliminate the risk. You can be the healthiest person in the universe. You can do lots of exercise, never drink or smoke, have a great diet. It's still possible for you to get cancer. You can be the unhealthiest person in the universe on the flip side, and you'd never get it in your life, and you can live to 120 years old. If you do those things that are risky, carcinogenic, and risk factors for cancer, you're much more likely to get it in your life, but it's all a matter of risk and chance, right?
Yeah.
So some of these are the classic things, eating and drinking healthy, or at least not overtly carcinogenic stuff like alcohol, although we all do that. Doing plenty of exercise, reducing your stress is pretty important. And some of the reasons some of these things work and help to prevent cancer is because they help your immune system to work. Because your immune system is actually patrolling your body all the time, searching for cancer cells. So there's that classic thing people say, which is true, that we all get cancer every day. Probably somewhere in our body every day, we have trillions of cells, and somewhere something goes wrong and we have a risky cell in our body, and our immune system will detect that and kill it. It's actually pretty good at doing that. So that's why we don't have any problems until later in life. Hopefully, most people don't get cancer till later because our immune systems are functioning and helping to prevent cancer from developing.
As an outsider, someone that is obviously not an expert, but as you said, as we live longer lives, there's just a higher probability for people to develop cancer, right? So probably because
Usually that's the case.
historically, our lifespan has expanded. We don't live 40 years anymore. So cancer now becomes one of the principal reasons of why we die. But as you mentioned, some of the more technical aspects, could you please mention what are the key components that we need to be aware of? Even if they're a little technical, but perhaps can be helpful. I know we're going to be talking about T cells, but what are the other elements inside our body that we should be familiar with?
Just before we say that, I want to clarify that sadly, there are many kids who will get cancer, and there are younger people who get cancer. And although it's more usual for older people to get it, it is definitely possible for younger people to get it. And that is definitely a possibility. And those things exist. And I don't want to sound like I'm negating the existence of those people. The classic things with cancer treatment is you have to look at the origin of the cancer. There are two things which really distinguish cancer apart from the rest of your body. So these are the two things that you have to focus on for an effective treatment. Number one, they divide really, really fast and out of control. Number two, they're very mutated. So some of their proteins may be different, or they might have more or less of certain proteins. And I suppose you could say number three, the tissue of origin means that you can exploit certain things about where the cancer originated from. Let's introduce the history a little bit. So the history of cancer treatment, for a very long time, it was pretty much just surgery. And even then, historically, if the tumor wasn't somewhere on the surface where you could see a lump, it was very difficult to even know it was there, let alone treat it. The reason things are called cancer in the first place is because they could only see the ones on the surface, and it looked like a circle with lines coming out of it, a bit like a crab. Same as the word for crab is cancer. And there's a really good book about this that I recommend that lots of people in the field love to recommend. It's called The Emperor of All Maladies. It's a great book.
What's the main storyline?
Yeah, it's a great book by Siddhartha Mukherjee. And it's an overview of cancer and a deep dive into the history and kind of current treatment methods. It came out in 2010. So it doesn't really have much of a section on immunotherapy, which we're going to talk about today, the kind of the next generation of cancer therapies. But it has a great information about the current state of the field when it was written and the history of cancer. So I highly recommend that if you're interested in this and want to know more. And it's really accessible as well. It's designed for people who aren't experts, who are interested in the field. But yeah, to paraphrase that book a little, surgery was basically one of the only treatments they had for a very long time, trying to cut out the tumor. Then chemotherapy was discovered in the 20th century. The first ones were based on the same chemical as mustard gas. And they noticed that it would actually kill fast-dividing cells, so they applied it to leukemia, and they noticed it worked to treat leukemia. So then there was a whole new field of chemotherapy.
Can you tell us exactly what type of cancer is leukemia?
Sorry, leukemia is a type of blood cancer derived from B cells. Leukemia means white blood cell, or cancer of white blood cell.
Perfect.
Yes, so the same as in another cancer, you have white blood cells will proliferate uncontrollably until you get cancerous white blood cells in your bloodstream. They don't exist as a tumor, they exist as individual cells floating around, but Eventually, you have so many of them that they dominate the cells in the blood. And you can see them under the microscope, which is one of the first cancers to be studied. And in fact, many of the pioneering cancer treatments like chemotherapy and radiotherapy, they all focus on leukemia as a first instance because it's quite easy to treat. It's almost like an introduction to treating a cancer with a new type of therapy. And actually, the same exact story follows for immunotherapy. But they developed this chemotherapy that became a whole field when they researched more and more and more compounds that worked against cancer. And the way chemotherapy works is these chemicals will disrupt the cells as they divide. Regular cells that don't divide as quickly and in a more controlled way can survive the chemo. They're not very happy with it, but they can live. Whereas a cancer cell, because it's dividing so quickly, it is not taking time to sort of pause or repair itself when it gets damaged, and it will just, it will keep dividing as it's being damaged, and it will just cause it to die because it can't repair itself. You can almost imagine it like a snowball of damage, and then it falls apart. Same thing with the radiotherapy. They discovered that radiation can damage cancer cells for the same reason. It blasts the DNA apart. Normal cells will repair that. Again, they won't be very happy about it, but they can survive it. But cancer cells can't repair themselves. They're dividing too quickly, and they're not repairing fast enough, so they get blown apart by it, basically. And this is some of the reason why when you get these cancer treatments, your fast-dividing cells in your body can also be damaged. Like your hair follicles are fast-dividing cells. Your hair falls out when you're doing the treatment. That isn't because of the cancer. That's because of the treatment damaging.
So chemotherapy will target all fast-dividing cells across our body, including our hair. Is that what you mean?
Including our hair, cells in the gut. It will damage us. But our bodies are quite resilient. And if you can destroy the cancer, your cells will recover from that at some point later.
And so my understanding is this old model of curing cancer is from the outside in. So whether we do a combination of surgery, radiotherapy, or chemotherapy, we're attacking the cancer from the outside in a very physical way. But now research has moved towards immunology, which is the idea of tackling cancer from within the inside of the body, if I understand it correctly. Can you expand on that?
Yeah, that's a nice way to look at it, I think. The immune system is our body's internal way of policing our cells. It can detect the difference between a self entity and a non-self or foreign entity. So the way it works is your immune system, when the cells are produced, they're trained almost like a filter. Think of the immune system as like a shape detector. Tiny protein-sized shapes are sort of detected by other sticky proteins that exist on the outside of your immune cells, kind of like a lock and a key. That's the classic thing we learned in school, right? And when the immune system detects a shape that it knows is not supposed to be there because it's been trained on what is you and what is not you by extension, think of it as a really powerful killer system inside your body. And any protein inside your body has been given a safe pass, but anything else is fair game to target and attack. Does that make sense?
Yes, it does. Okay. So it studies our body to understand.
In a sense, our body has systems inside it, when inside the cell-producing organs and glands where the cells are made. Basically, any immune cell that is produced, take the DNA that makes the immune cell receptors and detectors, and they shuffle them around, like randomly generating a number. They'll randomly generate a receptor. Now, then they test that receptor against the proteins in your body, which are just there inside the organ. Mm-hmm. If that immune cell reacts against any of these, it's killed before it gets released into the body. Anything else, it becomes an immune cell that is existing inside your immune system. And basically, they're waiting there for something to come along that receptor they've made reacts against. So you get a bacteria infection or a virus infection or a cancer mutation. If that receptor detects that shape that is not a self shape, it triggers a huge immune reaction that will destroy whatever is expressing that protein or shape. So the adaptive immune system is really powerful, very good at killing what it's supposed to kill. It's trained against the self. So cancer is made of the self. So it's quite difficult for the immune system to target cancer. Mutations that are obvious enough can trigger the immune system. But quite a lot of the time, cancer will, because it's made of your own body cells, firstly, it's not easy to target something made of yourself because the immune system's trained not to kill itself, right? As I just mentioned, it's literally trained not to kill itself proteins, which is the core problem here with cancer. And the other thing is that cancer, as it develops, it will get more and more mutations and more things that help it to survive. And eventually it will literally produce like a shell around itself sometimes inside the tumors that they can physically stop immune cells getting inside. They're like really low on oxygen and super hypoxic inside. So that means that there's like no nutrients for immune cells to work. Even if they do manage to get inside, they can express all kinds of things that like literally shut off the immune system called checkpoint proteins. So they can literally, the immune system has got these powerful immune cells that I mentioned have got like safeguards on the outside of them. So if your body thinks, oh, my immune system's been on too long, I've been infected for too long, and my immune system's actually causing more harm than good, they switch it down. They kind of switch it off. Or at the end of an infection, you have to tell your immune system to stop. Cancer can exploit those signals and tell the immune system to stop before it's actually had a chance to do what it needs to do. It's very, very clever. It's just developing them through random mix matching of mutations. And over time, it will get so many of these mutations that help the cancer out. It can kind of look like it's developed its own mind to do really, really interesting stuff to switch off the immune system and hide from it. Anyway, slight tangent there, but the immune system is, difficult to treat cancer because it's made of yourself. That's the key.
Okay. But I feel like the advantage that comes from the immunology approach is that now we can recreate a kind of self-coded approach that is different to every single individual, right?
Not quite. So there are therapies that exist in that way. So there are things like that, you could say. But the concept of immunotherapy is that for cancer, and again, you have to think of this as each individual cancer as a kind of different disease. But let's say for myeloma, for example, I used to work in a myeloma lab. There are proteins on the outside of a myeloma cancer cell that they're not necessarily specific to that cancer, but they are targetable by the immune system, right? So, for example, myeloma is derived from plasma cells. So you can target a plasma cell protein. That means that you'll obliterate all the other plasma cells in the body, but you can actually survive without those. So it doesn't, it's more important to destroy the cancer. This is an example of like finding a little difference that you can exploit with the immune system, because the immune system's so good at seeing tiny differences. If you can find a protein that you can target as an antigen, and antigen is just anything that the immune system can react against. If you can find a protein that you can target, you can turn that powerful immune system against the cancer. You can target individual pieces of it. We mentioned a few of these B cells and T cells, but what those actually are, they'll both react to an antigen or a target that they're being shown. But a B cell is a white blood cell that makes antibodies, sticky things, sticky proteins like a Y shape that float around in your blood. If an antibody sticks to something, it tells the rest of the immune system, kill me. Or if an antibody sticks to bacteria, for example, it can like clump it all up into a big blob that's easy to get rid of. T cells are the killer cells of your body. So if a T cell receptor detects its antigen target on the surface of some cell, it will kill that cell. Really, really powerful killer cells. So they will zap it with all sorts of killer proteins and force it to die. So the T cell will kind of go around scanning its surroundings, sort of touching the outside of other cells. And if it detects a protein, it will latch onto it and inject it with killer stuff to make it kill itself. So with immunotherapy, you can retarget those things towards cancer. So you can target a killer T cell against the cancer cells, which, as I've just said, is a really, really, really good killer cell. So it's quite powerful. And you can target antibodies against cancer cells, which are useful in a number of different ways, which we can talk about.
And I have a question. Obviously, when these anomalies start and we are at the first stage of cancer, it's really difficult to detect it. So can you just explain what are the different cancer stages, or at what stage it becomes easy to detect this type of anomalies?
So the stages of cancer from a immunological perspective, at least, or from my perspective, is you have the initial mutation, then you have a small cancer in one place where it doesn't really do much damage yet, but it's just sort of growing. And then it can progress a bit more, staying in that same place. And then eventually it will spread around the body. And that's when it gets dangerous and can be fatal and starts to be difficult to treat. When it's in the earlier stage of staying in one place, in situ, it's much easier to treat. It's easier to localize the treatment, and it's not as big, and you can see it and you know where it is. But when it starts to spread, and doctors will call this metastasis or metastatic cancer, that's when it's difficult because you don't know where it's gone. It's blocking things, it's traveling through the bloodstream or other places, and it's blocking this blood vessel and that. And that's when it gets dangerous and difficult to treat as well, because you have to do whole body treatments, which are really bad for you.
And so we have different treatments that are considered the main treatments, and they differ based on the stage of cancer, I'm guessing. Can you just explain us what are the main treatments that we use today?
Yes. So the main treatments we use today, the oldest one and maybe still the most common one is surgery. Although, again, I just want a disclaimer that I'm not a doctor, so I'm not the person who treats cancer. I'm just the one who researches new treatments. But in my understanding of the field, surgery is the one which is most common still, and it's where you can see the cancer in one place and you can remove the tumor and the cancer tissue, maybe do a small round of other things like chemotherapy just to make sure you've got all of the cancer cells out and you physically removed the cancer, so it's gone. The other one is chemotherapy, and maybe we should group this together with radiotherapy because the way these work, these are chemicals or radiation that exploit the cancer's growth rates. You either chop it physically out or you exploit that fast growing dynamic that separates it from a healthy tissue.
Mhm.
These are the traditional ways that we've seen the difference between cancer and healthy. And they're still really, really common and very important parts of cancer treatment. Like they're never going away. They're still going to be the cheapest, most effective in many cases way to treat cancer. But now we've got these new therapies that actually exploit a different difference between healthy and cancer cells.
Okay, yes. And my understanding is that in this old school 3-step process of surgery, radiotherapy, and chemotherapy, you need to usually combine 2 or more of these options depending on the size and the location of the cancer. Is that fair to say?
I think so. Again, I'm not an expert on clinical plans for cancer treatment, but as I understand it, you often combine them. So, for example, a surgery can remove 99.9% of a cancer, but if you have like one cell left in the body, eventually it will come back and cause another tumor. So, to make sure that they get rid of everything, they might give you surgery to get rid of most of it, and then one of these other ones to kind of try and remove any cells that might be lingering behind in the sort of patient without noticing it as you do the surgery.
And now we have this new emerging field, which is the one that you're focusing your research in, which is immunotherapy. So how
Yep.
is immunotherapy different?
So this is basically a whole new paradigm of cancer treatment because it works on a completely different basis to see the difference between cancer cells and healthy cells. So what we do, or what the field does, I should say, is instead of trying to see the differences in behavior of the cancer cells, they look for specific molecular protein-based differences on the outside of the cell, and they exploit the immune system's ability to target specific antigens. An antigen is just something the immune system can target, like a protein or a shape, some kind of thing it can detect. The immune system can detect antigens and kill the cells which express or have that specific antigen on the surface. Our body has this system inside it already. It's really powerful. It's really good at killing things and destroying stuff that's not supposed to be there. So immunotherapy harnesses that to kill cancer. And how does that work? It basically tries to find any tiny protein difference on the surface of the cancer cell between a cancer cell and a regular cell, a healthy cell. That could be a mutated protein. It could be a protein that's expressed more or less than usual. Or it could even be something like a regular protein that's not in the right place. So a lung protein that's in the liver shouldn't be there, so you can see that, right?
And I'm trying to visualize this as a table of old school methods against immunotherapy, right? So I'm thinking that the first one is physical, and it sounds like it's a one-on-one process. I feel like surgery definitely is. So the doctor needs to actively spend time with the patient to carry out the surgery. And then we have the costs, and then we have, to some extent, the passive work that gets done. If you do a surgery, there is no passive work that gets done. You need to rest. The cancer doesn't get cured while you rest. Is this different with immunotherapy?
Yeah. So imagine your immune system tackling a disease, right? It works very specifically. It won't damage healthy tissue, or you feel symptoms of a disease. Ultimately, your immune system is specifically going after the bad things in your body. And when you get an infection, you're then immune to it. So your body learns that it's been infected or damaged by this infection or a cancer that's been inside its body, and it creates a memory. So you've got memory cells in your lymphatic immune system, and they're basically waiting there to reactivate really quickly if they ever see the same thing happen again. Your immune system is kind of primed to go after the same thing if it ever comes back. So, and by the way, your immune system is constantly hunting for cancer. Like we have many, many anti-cancer mechanisms inside our immune system as naturally just in us. We have these cancer detecting systems in our immune system. And that's one of the reasons that if we can get an immune therapy, a therapy based on the immune system, it can specifically attack cancer at a protein level difference. The cell could be identical to a healthy cell apart from having one tiny mutated protein on it, and we could target that protein specifically. It's a way to really accurately and specifically target things. And then you can also have a long-lasting memory that lasts for a long time after the treatment and protects you going forwards. Not with every single immunotherapy, because this is probably quite a big field that works in lots of different ways, but for some of them, you can have memory.
So the main difference, I feel like, is that we now have trained the immune system to do this job for us on a continuous basis.
Kind of, you could say that. I mean, immunotherapies work in a couple of ways. So you're either kind of like unleashing your immune system that's already in your body to work better and to actually work against the cancer, or you're kind of reintroducing a modified immune cell or immune antibody or anything derived from the immune system to work against the cancer that you've kind of made in the lab or derived from the lab. So you've specifically found something in the lab that kind of sticks to the cancer proteins. You've put that onto the surface of the immune cell and then put those cells back into the body. That's kind of the principle of adoptive immunotherapy versus the type where you unleash the immune system that's already sat there in your body waiting to go. Kind of the two sides of it.
Okay. And this is what you do in your research. So CAR T.
Yeah, exactly. I'm a CAR T cell researcher.
What does CAR T stand for? What are we talking about? How does it work?
Yeah, it's the kind of thing that will blow your mind, but takes a little bit of preamble to get there, okay? So everybody knows we've got white blood cells in our blood, right? Some of them kind of just, when they see something wrong, they'll just eat the bacteria or the infection or whatever. But some of them have these very specific receptors on them that can detect and destroy very specific protein targets. So one of the types is called a B cell. These make antibodies of sticky protein shaped a bit like a Y, and the short ends of the Y are very sticky, and the long end has got signals on it that tell the body to eat or destroy whatever it's stuck to, right? And a T cell will scan around, it will kind of swim around and scan all the cells around it. And if it detects one that's infected or cancerous or got bacteria inside it, it will latch onto that cell of your body, and it will inject it with killer proteins and destroy it. It will force the cell to die. You can almost think of it as the body's police. If it detects a compromised cell of your own type, but something wrong with it, it will scan it, see it, and force it to die to protect the rest of the body. So those are the two types of white blood cell that make the adaptive immune system. So these are the two that we often talk about in immunotherapy because they're the most powerful type of immune cell, and we can program them. That's the key thing, right? So CAR T cells, you take a T cell and you put into it a new protein. This protein has an outside bit and an inside bit. So the outside bit sits on the surface of the T cell. This outside bit, it's usually made of an antibody, by the way, so it's just a sticky thing. It's just a sticky thing on a stick. And it will stick to a cancer protein. And the inside bit is the signals that tell a T cell to kill whatever it is that the receptor binds to. So I said that T cells have got these receptors on their surface naturally. We pretty much just cut and paste the signal from that natural receptor and splice it onto a sticky outer binder that can grab onto cancer proteins. And when that binder grabs onto the cancer protein, the T cell will kind of tug on it, and it activates the same signals and process inside the T cell as it does in a normal T cell when it scans for its prey. And that CAR T cell will then kill the target cell in exactly the same way as a natural T cell will kill its target. And by the way, CAR means chimeric antigen receptor. So it's chimeric because we've glued two proteins together. It's an antigen receptor because it's detecting a protein that the immune system can see. That's all that means. So chimeric antigen receptor will detect a protein, and we tell it which one to detect because we made the protein, right? We made the sticky end. You just take an antibody for anything you want and glue it to that. So we program the T cell with that specificity to whatever we want. And then you put those T cells back into the patient. So you take them out in kind of like a blood taking. You modify them in the lab. There's various ways you can do that. You can do that with viruses. Viruses are basically just tiny things designed to inject DNA into cells, right? So we can put our DNA into the virus and then add it to the cells. Or we can even just literally zap the DNA directly inside the cell with an electric pulse. That works as well, by the way. There are tons of ways you can do this. And then you put the cells back into the body, and now you've got a T cell which, instead of attacking its original target, we've reprogrammed it with that sticky protein to attack what we want it to attack. It sounds maybe more simple than you might expect, but it works incredibly well because these cells are very, very powerful. And when they see their target, they proliferate. So they grow millions and millions and millions of times, or they divide millions and millions of times, and they just fill the blood with all of them. So if you've got a cancerous cell or cancerous cells inside your body, you can imagine that this is a great way to kind of make sure you clear your body out of any cell that has this protein on it, right? Now, the difficult thing is, how do you find a protein that you can target? How do you find something on the cancer cell that is targetable such that you won't suddenly start killing your own healthy cells with the T cell?
Okay.
That's the challenge.
If the training goes wrong, then there is the risk that you're destroying cells that are not cancerous cells.
It's more like once we add this receptor to the T cells, it's very specific. So there's not really any chance of it attacking the wrong thing. The problem is, how do we find the thing to attack? Because as I mentioned, cancer cells are pretty damn similar to regular cells, but they usually have something that you can exploit. For example, leukemia is pretty easy because leukemia actually comes from B cells. It comes from white blood cells, right? But B cells have got a protein on the outside of them that only exists on B cells, so it doesn't exist anywhere else. And you can live without B cells, actually. So if you target that protein, you can wipe out all of the leukemia cells. And yeah, you will also wipe out all the B cells, but you'll be cancer-free. So I think it's a worthy trade-off, right?
What would be the worst outcome once you have no more B cells? Because B cells, then they are creating these antibodies that get attached, right?
Yeah. I mean, the worst case scenario is that you have to take antibody supplementation for the rest of your life, but it's a lot better than dying of a disease, I think. By the way, I should mention at this stage that it's not a miracle drug. There are complications from it. And by the way, they're pretty good at managing those side effects now. So don't be put off from getting the therapy just because I said that there are some side effects. They know that they exist and they give you medication to stop them happening. But that's just to say that CAR T cells do have risks and side effects associated with them. That's all.
Yeah. So CAR T cells are just one of the many types of immunotherapy. What are the other types that we should be aware of, and how do they differ?
I think you can class these into two categories, really. You can class them into helping the immune system that already is in your body to work better and reprogramming things manually, I guess you could say, outside the body in the lab, right? So there's a therapy called TILs, tumor-infiltrating lymphocytes. This is where they take white blood cells that are already inside the tumor, because your body is trying to battle against it, even if it's not winning that battle. They take those immune cells out of the tumor and they simply grow them in the lab until there's many more of them and they put them back in your body. Because those cells inside the tumor are already reactive against the cancer. They're just not enough of them to do the job properly, right? Or there's something stopping them from working completely. So that's one type of immunotherapy that's relatively simple. Even just using an antibody, because we can produce monoclonal antibodies in the lab for decades now. That is a type of immunotherapy because it's based on an immune protein, right? Antibodies. Your body makes these to fight against infections all the time. So we can make them in the lab pretty easily. And if you make an antibody against cancer, for example, daratumumab for myeloma, it sticks to the outside of the myeloma, and that simply tells the immune system, hey, look, come and kill this thing, right? That is a simple but effective type of immunotherapy. There are other things, so checkpoint blockade inhibitors. So this is a type of mutation that cancer gets where it will try and switch off the immune cells by interacting with their switch off buttons. So immune cells have got switch off signals on them. For when the infection's finished in a normal reaction, your body kind of tells the immune cells, right, you don't need to keep going, time to stop, right? The cancer can do that too. So some cancers, they mutate, they make new receptors, and they start to realize that, oh, if we switch off the immune cells, then we can grow more. So those cancer cells become more dominant, and eventually they fill your body with these mutations. So if you have an antibody that stops that protein from attaching to the immune cell and telling it to stop, you've now unleashed the immune cells again. So the immune cells haven't got this stop signal anymore. Then they start working again, and then your normal immune system can still work. You don't have to engineer them with anything. You can just unleash the ones that are already there, right? And on the other side of the coin, you've got these engineered immune therapies where you Well, you've got something in the middle. So you can have cancer vaccines, and you may have seen that this is a thing. It sounds a bit strange that you could vaccinate against cancer, but you can, because vaccines, and all they're doing is you're telling the immune system to react against an antigen. If you do the same thing with a cancer antigen, you can vaccinate against cancer. It is definitely possible to do that. All you need to do is introduce a strongly activating signal with the cancer protein, and you can train the immune system inside the body to fight against the cancer in a more natural way that you're more familiar with. Look, we all know that the immune system reacts against proteins it doesn't like and creates an immune response and then a memory, right? You can do that with cancer proteins. Why wouldn't you be able to? And then you've got the ones where we directly reprogram cells with an artificial receptor to almost brute force them to attack what we want them to attack, which is more the CAR T cell side. And maybe that can lead into the CAR T cell explanation. But the CAR T cells are very, very powerful, but they're very brute force, and they're very expensive to do it that way. Like taking a cell out of the body, engineering it, and then putting it back in. This can cost $500,000 to $1 million a patient for some of these treatments.
So out of all these different technologies, which ones are the ones that we can expect to revolutionize the world of cancer? You just mentioned that if we're going down the path of some of these technologies, it would cost almost $500,000, which is probably not what most people are willing to pay to cure cancer.
No. Well, if we want to start maybe with the idea that the simpler the better when it comes to implementation, right? So some of these things are now becoming very standard treatments, like the antibody therapy, used all the time in various different cancers, right? And it's maybe not as massively groundbreaking and as effective as some of these cell therapies, but it's still a massively useful tool in the arsenal of doctors to use this, right? Whereas things like CAR T cell therapy, they're so difficult to make and research and produce, and it just takes ages to sort of validate them. There's a few of them now that exist on healthcare plans and things, like the original ones were called Kymriah and Yescarta. These are the original CAR T cells targeting blood cancers. Also, by the way, I should say, they don't really work in solid tumors at the moment. So they have had some success, but it's a bit hit and miss, and we're not quite sure how to consistently make them work really well against solid tumors.
So all immunotherapy cures don't work on solid tumors, or just?
No, this is just for CAR T cells, but solid tumors are just generally a lot more difficult to treat than liquid tumors anyway. Immunotherapy is such a big field that there's lots of different things you can talk about, right? I mean, the simpler the better, and there are some that are antibody-based that are much easier to make. So you have these, and by the way, antibodies are so diverse, you can use them for lots of stuff. Like you can even use them for chemotherapy, combining immunotherapy and chemotherapy, attaching a chemical chemotherapy onto the end of an antibody so that it only affects the cells that the antibody sticks to and not the rest of your body. So it's almost like delivering the chemical directly to the tumor and trying not to make it stick anywhere else. So it's a little bit more safe than regular chemotherapy. Or there are other things. You can attach like a glowing protein onto the end of the antibody. Mm-hmm. The antibody sticks to tumor cells. In the surgery theater, the doctor can wear glasses that illuminate the glowing protein, and you can literally see the tumor glowing. So any cancer cell will be glowing bright, and the healthy tissue will just be dim. And that helps the surgeon to precisely chop out the cancer cells and not leave any behind and not damage healthy tissue. I mean, they don't need to, right? So these are some of the ways that antibodies can be used and are being used right now, because they're pretty easy to make these. Mm-hmm. The more complex immunotherapies, I think they will revolutionize it. They're going to get cheaper and cheaper, by the way. They're already working on ways to reduce the cost of these immunotherapies. And that's one of the big focuses of the people who make them, by the way. But they are a bit more tricky to get over the line, because you're literally directly genetically engineering a cell and trying to use that as a medicine. It's quite different to what's been used in the past as any kind of medicine, right? But when it is ready, it's going to be able to not just cure cancer, it's also curing autoimmune disease in a huge revolutionary way. You know, lupus, myasthenia gravis, all of these things that we could never treat are now absolutely treatable by CAR T cells. We just need to get everything approved and ready and get the costs down. And in my opinion, these are going to revolutionize not just cancer, but also autoimmune disease, maybe other things. We've essentially got the ability to program powerful cells of our body to do things now. And you can imagine what that means for treatments of very many diseases.
But if you had to pick one of the many immunotherapy ideas that we just described, what do you think the future of cancer treatment will look like? Will it be a combination of all of them, or is there a few that stick out as the most prominent and promising technologies?
I think as a CAR T cell researcher, I'm inclined to say that CAR T cells will be the revolutionary cancer treatment that changes the field once they get going and the ball gets rolling with them. And also, they're becoming more and more easy to sort of skip onto another cancer and modify them slightly and make them way cheaper. There's this whole new field called in vivo generation. So instead of making them outside the body, you give somebody an injection that inside your bloodstream will just make your white blood cells start producing this receptor. Again, it's tricky to make this happen and make it work as a certified medicine. But, can you imagine when that gets approved? You just go to the GP and get an injection from the fridge, and they'll be, oh, yeah, let me just make your immune cells kill cancer. Here you go. You should be cured within a couple of weeks.
Yeah,
That's
that is
the dream.
incredible.
That's the dream. I mean,
World-changing technology. How many years into the future will this happen, and how expensive will it be?
Well, as I say, the antibody-type therapies like checkpoint blockade inhibitors and some of the other ones, like just monoclonal antibody treatment, these are being used right now, and they're very commonplace, and they're pretty cheap. Things like the CAR T-cell therapy, they are being used, even in the NHS, for certain conditions, but they are very, very expensive. They're like hundreds of thousands of pounds per patient.
This is at the moment.
This is, as I say, people are working really hard to get those costs down. These things work pretty slowly. So I think you maybe see another 10 years before this stuff starts to become more commonplace. And it's a bit like slowly turning the temperature up. You don't really notice it until it's everywhere. So one day we're probably going to look around us and be like, oh, it's pretty easy to get revolutionary immunotherapy in the hospital these days. I mean, we didn't even have a news story about it, I think it's going to be one of those things that creeps up on us until we realize 20 years later that we've got thousands of these new treatments everywhere, relatively easy to access. And suddenly we've got a whole new world of cancer treatment to 20 years in the past. So I think in 20 years' time, if we look back at current treatments versus then, it's going to be so different. It's going to be the biggest revolution in cancer treatment in ever. But we're at that stage now when all these things are being tested and going through this really slow regulatory process where you have to be approved here and show that it works. And if it doesn't work, you've gone through all the clinical trials and then you try it and it doesn't work as good as that. It can tank the whole thing. We're getting through those barriers, but once they become cheaper and a bit more consistent, let's just say it's going to be completely game-changing for cancer therapy. Probably we're just going to combine all of them. You give somebody surgery to get rid of most of the tumor, then you give them a CAR T-cell dose to destroy all the cells and have a memory response, maybe a radiotherapy blast to get rid of the rest of the tumor mass at the site, and then the CAR T-cells can be the longer-term memory-induced state where the cells will last for a long time, years. They'll be in your body, making sure the tumor doesn't come back. So you can imagine a world where we combine these things together, how effective that could be. I don't think we're ever going to cure cancer, because as I say, it's a very diverse disease, but we're going to get a lot better at curing a lot more people. And we're going to get to a world where maybe cancer is a dangerous, but usually manageable disease rather than a really dangerous. And
you can correct me on this, but I feel like CAR T gives us a generalized approach to solve different types of cancers in different people, in different location, at different stages. So all of a sudden we have these 200 plus variations of cancer, in different stages and different locations of the body. And now all of a sudden there is one solution that automatically modifies itself to help us solve majority of these.
Not quite.
Different. Okay.
That's not quite
Why
right
is that?
because, as I mentioned, every cancer is different. They don't all have the same antigens on the surface. So if you have to choose an antigen or a target, this cancer has got a totally different set of antigens to that cancer. And while myeloma or leukemia may usually have the same proteins on the surface, not always, but mostly, it will have a totally different set of antigens that can be targeted than lung cancer or brain cancer, right? So actually, it's more accurate to say that as a concept, we can apply it to every cancer, but each one needs to be kind of developed on its own. And by the way, you can randomly have like a leukemia that doesn't have CD19, the most common antigen. So all of a sudden, our treatment that we've developed doesn't work for this patient,
Yeah, there is. Okay, so I'm guessing that some extreme case scenarios might still be extremely hard to work on.
Well, it's probably going to be more common than extreme fringe cases, but it's probably going to be the majority of people will fall under some kind of CAR T-cell treatment bracket, I would predict, once they've been developed. But not everybody, but most people will be under one. And if we can get the costs way down, and if they're a weak patient or they're frail and they can't tolerate like a big immune response in their body, they might not be appropriate for the treatment. Or if their immune system's weak and damaged, that means that their T cells won't be very good quality, which means that you can't really turn them into CAR T cells. So there are reasons why it wouldn't work for everybody, right? If your immune system is not strong enough to produce CAR T cells that would kill cancer, then it's not a treatment that would work for that patient. That's all I mean to say.
Yeah, that makes sense. If we look at the cancer treatment researchers space, what is the vision that all the researchers have about immunology, CAR T more specifically? Where do they think the world will end up when this technology will be around? Will we expect most people to live past 100 years old and not die because of cancer? Or what would the world look like if we could cure majority of cancer diseases?
Well, that's interesting because cancer is one of the big killers as you get older and older. But I think if we can cure many cancers, I think you will obviously eventually die of something else, I think. But I mean, it's an interesting idea, really. I mean, this is slightly going off topic, but there are many people focused on things like age-related treatments and reversing aging. And obviously, I'm focused on cancer research, but I'm sure there are many people focused on heart disease and other things that... So you could imagine a world where actually we're pretty good at treating most illnesses, and we're also pretty good at de-aging people. I mean, it's not great for the population crisis, but it's pretty good if you're somebody who wants to live a long time. Yeah, I mean, you could probably imagine people living to the classic sci-fi trope is 150 to 200 years old becomes the new age expectancy. Something I haven't really mentioned yet, but is very important, is that we're very good at detecting cancer, or at least screening for risk factors now. So if you have a gene that makes you more vulnerable to it, we can detect that in your genome and make sure that you are screened properly and catch the cancer earlier if it does happen. So we're also getting better at detecting it and preventing it in that sense through technology advancements. So yeah, all round, we're getting a lot better at detecting it, preventing it, treating it, curing it sometimes, more and more. So it could become a case where it's a dangerous but treatable illness rather than a deadly one for many people. Yeah. The other thing is that as it's expensive, right now, there are concerns about accessibility and, wealth inequality with this, because if the Western world can make cancer treatments that cure them, but the rest of the world cannot afford the huge costs of these treatments, then if medicine turns into a situation where you have massively expensive but very effective treatments, then it's really a tough question for healthcare systems to prioritize which patient over another if the treatments are really expensive or not. But B, it's not a great look for international, developing countries not getting access to the best treatments that are available if they're so expensive. As the costs come down, that might be less of a problem than it looks right now in the early stages of research. But it's still a concern to me that everybody gets access to these medicines, because I don't want it to be a world where the West gets ultra good cures and the rest of the world has to just watch from the sidelines as they still suffer from the same diseases as always.
One of the things that we haven't touched on, which latches onto what you just said, is that as you do research in a university lab, all the research is published. And so I'm assuming that any breakthrough technology or innovation that comes out of the lab will be made accessible to most institutions and hospitals, whether they're private or public. But when we actually look at who owns the technology and who can make the operations, where do we stand worldwide? Is it mostly Western countries that have these technologies provided from public hospitals? Or is the technology broadly available to any private hospital? I'm not sure.
Yeah, the equipment that you need to make this probably costs $500,000 to £1 million for a basic lab. And if you want to make this GMP, which is, that's a technical term to say good manufacturing practice quality, which is what you need for a medicine, at least in the UK for sure. It's extremely expensive to make things to that quality, especially things that you need for genetic engineering, like viruses and cells grown for many weeks in this kind of quality lab is just absurdly expensive. This is where all that cost comes from. And this is why it costs £500,000 per treatment, right? That's where that comes from. It's the cost of the reagents and the process for manufacturing these therapies in a system which is medical grade. Because what you really don't want to do is to make it in a sort of a shoddy lab, inject it into somebody, and then they die of sepsis because they've been infected with a bacteria during the manufacturing process because you haven't done it cleanly enough, right? Or you've caused some other issues for the same thing. So they have to be made really, really, really high quality. So to set up one of these labs is very expensive. Although that's not to say that it's impossible. And I saw a really cool article a couple of years ago now, I think, where some lab in India had managed to manufacture medical grade CAR T cells for a tenth of the price of the West. So it's definitely possible to bring those costs down. And in fact, some of the other things that I talked about, like the in vivo generation, which is to say making it in your blood instead of outside in the lab through various techniques, that's, I don't know, a tenth of the cost. So much, much cheaper.
Mhm.
So these various different innovations, it's driven by demand and market forces in a way, isn't it? As many things are. If it's something that can be sold around the world, there is a drive to make this as cheap as possible and as accessible as possible, right? Also, you talk about these pharmaceutical companies sometimes, not you personally, but people talk about these pharma companies as if they're these money-hungry, demonic people. But actually, most people in these companies just want to make treatments and help people. They're same as any other researcher, right? So there is a drive to make this stuff as accessible as possible from a non-profit based incentive, is what I'm trying to say. People just want to help and cure people, no matter where you work. So
Yeah, I'm just playing devil's advocate here. I don't think that people are directly accusing the researchers within the labs. I'm sure that they have really good motivations and they're driven by the interest to change the world for the better. I think the accuses are mostly pointed at the business models that priced some of the medicines with massive margins compared to the production costs. So I don't think
yeah,
that we're necessarily referring to the researchers, perhaps more to the executives or business
I've
model of some of these
I've
companies. But I could be
seen
wrong.
some of these stories. Yeah, I mean, especially in the States where they make these medicines vastly more than the cost, as you say. But in the CAR T cell world, there genuinely is a huge production cost with this stuff. And
Yeah.
from my
I
limited
actually
experience in pharma, I saw these executives, they just wanted to help people also, for the most, their main driving force. I mean, of course, they were trying to help the business, but they also wanted to help people. So there is that incentive in these people also, I think. And I also think that, yeah, the cost of a CAR T cell is, I don't know if it's exactly at cost that they make this, but there's not a huge amount of profit injected into that hundreds of thousands of pounds manufacturing cost that I mentioned. That's just what it costs to make them.
No, it's good to know that at least from you that have worked in this space, that you feel like that the motivations behind, even the managers higher up the business are usually genuine. But I was actually interested on the CapEx and OpEx model that you mentioned. If most of the cost then goes into the capital required to build the lab and have all the different machineries to test all the CAR T cells, compounds, molecules, proteins.
Well, yeah, proteins, molecules, I suppose, sequences, DNA sequences, that kind of thing.
Is the OpEx cost something that can be averaged out as the economy of scale develops? So do you think it
Yeah,
will become
probably
cheaper the
true.
more people get the treatment?
Maybe. The way it works, the reason it's so expensive in the first place is because for every patient, you need to take their cells out, manufacture them, put them back into the patient. So it's difficult to kind of mass produce them.
Okay, so that step is not scalable then.
It is. There are ways to try and do it. It's really difficult, but some people try and research stuff called allogeneic therapy, which is where you can give other people's cells to another person, but it's tricky to do that because your immune system will try and reject it. So it's a hard thing to do. Some people try. The in vivo way is another way to mass produce the actual. So in that case, all you need to do is mass produce the vector that you inject into the person. So you don't need to mass produce cells. You just need to mass produce the injection, whatever that may be, virus or mRNA or whatever it is, right? That's a lot easier to mass produce. So yeah, there is an economy of scale. And as you say, that's the way it goes. That's the way the field is going, trying to make this as cheap as possible by manufacturing something at scale, at least, to take the cost down instead of a bespoke treatment for every single patient, which is kind of what it is right now.
Mm-hmm.
You can still have you've developed a protein that works when you put it onto anybody's T cell. So in that sense that it is a uniform treatment that's given to anybody rather than every single person gets a brand new protein developed for them. No, the protein is the same, but you still have to take their cells out, modify them, put them back in. It's just expensive to do that. But if you can manufacture something in that process mass produced, either you make the cells compatible with other people or you make the in vivo one work better, that's an early development thing. If that can be developed more, I think that's the way the field's going to go, to be honest, the in vivo generation. Or maybe there are other ways you can do it. I don't know. Maybe they can make it cheaper to do the manufacturing step just by optimizing it more. But you can replace reagents. You can take an expensive one and replace it with a cheaper one. There are things you can do. The field will develop. I think it will get more and more. This is at the end of the day, it's a treatment that we can use to treat and maybe even cure people who have no other options, and to treat diseases that are extremely damaging to society and to people. So I think it's a great technology, and it's so great that people are going to find solutions to these problems. It's just going to take another 10 years. We're still in the early days of it. And I think it's going to be, in 10 years' time, we're going to see this everywhere. But it will be a slow burner. You might not even notice.
Mm-hmm.
I think that the key takeaway here is that we've got this new therapy type it works differently to the old ones that we're familiar with from the past. It's really interesting and powerful, but it's really expensive. And hopefully they find ways to make it more accessible to everybody as this technology gets better and better. And it gets implemented more and more around the world, I hope. That would be my hope. I mean, I could always mention my research is about studying the CAR T cells and how they work in a bit more detail. So we know that they work, but we don't actually know exactly how they work because they're very different to a normal T cell. We know that they're different and that they work differently, as in the signals inside them are pretty different to a regular T cell, actually. And yet they still kill what they need to kill. So people don't really worry about that too much. But my research is trying to focus on how they work in a bit more detail, like the signals that they have versus a normal T cell. And the hope is that if you understand that a little bit better, you can design a better protein to activate the T cells even more powerfully than they are already. I think the way that we're going to make this work the best is to understand how they work better, because really our understanding of the immune system is quite new. We didn't even know what an antibody was until the 60s or 70s. And now we're able to manipulate it in all of these ways. I think it's quite fascinating that we've gone from only finding the structure of DNA a few decades ago to now being able to introduce it to a cell and manipulate an immune system to target a target of our choice. And these things sound crazy. There's so many more things I could talk about, like base editors and CRISPR and gene editing and things like that. But it's such a big and diverse field that it's hard to mention everything. And if anybody has any questions or would like a part 2 or a deeper dive into any of these things, I think that would be also a fun episode to do. So let us know if you have any questions or things you'd like to hear more about. I'm sure I've bamboozled Fede enough today to bamboozle the rest of the audience just as much. So let's see if anybody has questions.
I really enjoyed this discussion. I think just preparing questions for this podcast was extremely interesting. There is a field that is so unknown to me and probably to most of the listeners. And I think that the type of research that you're doing is extremely interesting because for the first time, or one of the first few fields where we move away from physically doing a surgery to then just encoding instructions into the body. And not only we're doing this, but we're solving the biggest cause of death in the world. And we are now, I think this is honestly incredible. And I think everybody should at least be familiar with the field because the odds are that we might need to either treat cancer for ourselves or we'll know someone that will be in a situation similar to this.
Absolutely. I mean, I find it fascinating as well, of course. I never really was passionate about what I did before I found this subject, so I'm glad I did. And the thing I love about it is that I can experiment with crazy ideas as well, because it's such a new field that there's room to play with random ideas and you can test silly stuff. Most of it doesn't work, but when you find a random thing that does, then you feel pretty good about it because you're a pioneer at the early stages of something, right? That's why I like it.
Well said. Yeah, couldn't agree more.
Well, thanks for the questions, Fede. That was I enjoyed discussing it. I could talk about this all day.
Yeah. Thank you for taking the time. And I encourage anybody that has questions to put them as well on the podcast. And you can take them and we can do a round 2 and answer more specific questions from the audience.
Round 20. Let's see how many.
Perfect. Yeah. We're going to do a podcast just for immuno.
Yeah, we changed the topic. All right. Well, thanks very much, everybody. Catch us next time on Two Humans, and we'll see you next time.
See you in the next one. Bye-bye.
Bye.